many occasions in which the comparisons among means are more complicated than simply comparing one mean with another. This section shows how to test these more complex comparisons. The methods in this section assume that the comparisons among means were decided on before looking at the data. Therefore, these comparisons are called planned comparisons. A different procedure is necessary for unplanned comparisons. Imagine a hypothetical experiment in which 12 subjects were randomly selected from a population of high self-esteem subjects, and an additional 12 subjects were randomly selected from a population of low self-esteem subjects. All subjects then performed a task. After they had completed the task, half of the subjects with each level of self-esteem were told that they had succeeded on it, and the other half were told that they had failed. This feedback was independent of how well they had really done. After receiving this false feedback, subjects were asked to rate, on a 10-point scale, how much of their outcome of success or failure they attributed to themselves as opposed to being due to the nature of the task. Now look at the data. The first column contains the subject numbers. The second column is the outcome variable. Participants who were told that they had succeeded were marked with a 1, and participants who were told that they had failed were marked with a 2. In the third column, participants with high self-esteem were indicated with a 1, and participants with low self-esteem were indicated with a 2. The final column is the dependent variable, the attribution rating. For example, subject number 3 was a high self-esteem subject who was told that he or she had succeeded on the task. Overall, there were 4 different self-esteem outcome combinations, and there were 6 subjects in each of these combinations. There are several questions we can ask about the data. We begin by asking whether, on average, subjects who were told that they had succeeded differed significantly from subjects who were told that they had failed. The means for subjects in the success condition are 7.333 for the high self-esteem subjects and 5.500 for the low self-esteem subjects. Therefore, the mean of all the subjects in the success condition is 7.333 plus 5.500 divided by 2, which equals 6.417. Similarly, the mean for all subjects in the failure condition is 6.333. The difference between these two means is 0.084. The question is, how do we do a significance test for this difference? The first step is to express this difference in terms of a linear combination of a set of coefficients and the means. This may sound complex, but it is really pretty easy. We can compute the mean of the success conditions by multiplying the means for the high and low self-esteem subjects by 0.5 and then adding together these numbers. Here we see that for the success conditions, we compute 0.5 times 7.333 plus 0.5 times 5.5, which equals 6.417. Similarly, we can compute the mean of the failure conditions by multiplying each failure mean by 0.5 and then adding the results to get 6.334. By distributing the negative sign, you can see that the difference between the overall success mean and the overall failure mean can be computed by multiplying each success mean by 0.5 and each failure mean by negative 0.5 and adding the results. In this table, the coefficient column is the multiplier, and the product column is the result of the multiplication. If we add up the 4 values in the product column, we get 0.083. This is the same value we got when we computed the difference between means previously, within rounding error. We call this value L for linear combination. Now, the question is whether our value of L is significantly different from 0. The general formula for L is shown here. C sub I is the ith coefficient, and M sub I is the ith mean. As just shown, L is the sum of each mean times its coefficient and equals 0.083 in this example. So is this L value of 0.083, which represents the difference between the success and failure conditions, significant? We have to calculate the standard error of L before we can know. As you can see from the equation, this means we have to know the sum of the squared coefficients, the mean squared error, MSE, and n, the sample size. The sum of the squared coefficients is 1. In this example, because all of the cells have the same number of participants, MSE is the mean of the variances, which is 1.625. The value of n is the number of subjects in each group. Here, n equals 6. Using the values, we determine that t equals 0.16. We have to know the degrees of freedom in order to compute the probability value. The degrees of freedom is n minus k, where n is the total number of observations, 24, and k is the number of groups, 4. Therefore, the degrees of freedom is 24 minus 4, which equals 20. Using the online calculator, we find that the two-tailed probability value is 0.8745 when t is 0.16 and there are 20 degrees of freedom. Therefore, the difference between the success condition and the failure condition is not significant. A more interesting question about the results is whether the effect of outcome, success or failure, differs depending on the self-esteem of the subject. For example, success may make high self-esteem subjects more likely to attribute the outcome to themselves, whereas success may make low self-esteem subjects less likely to attribute the outcome to themselves. To test this hypothesis that the effect of outcome differs depending on self-esteem, we have to look at the difference between differences. Specifically, is the difference between attribution ratings given after success and failure outcomes by the high self-esteem subjects different from the difference between attribution ratings given after success and failure outcomes by the low self-esteem subjects? This table shows the relevant means. The coefficients that can be used for testing this hypothesis are 1, -1, -1, and 1. If it is hard to see where the coefficients 1, -1, -1, and 1 came from, consider that our difference between differences is computed by subtracting the difference between the success and failure groups for the low self-esteem subjects from the difference between the success and failure groups for the high self-esteem subjects. Notice how these formulas compute this difference. The subtraction sign reverses the signs of the means of the low self-esteem group. The values in the parentheses in the second to last line are the coefficients. This equation sums to 4.83, so this is our value of L. We will now continue the calculations to determine if this L value is significant. The sum of the squared coefficients is 4. MSE and n are the same as in the previous example. Putting it all together, we find that t is equal to 4.64. The two-tailed p-value is 0.0002. Therefore, the difference between differences is highly significant. In a later chapter on analysis of variance, you will see that a comparison such as this is testing what is called an interaction. In general, there is an interaction when the effect of one variable differs as a function of the level of another variable. In this example, the effect of the outcome variable is different depending on the subject's self-esteem. For the high self-esteem subjects, success led to higher self-attribution ratings than did failure. For the low self-esteem subjects, success led to lower self-attribution ratings than did failure. The more comparisons you make, the greater your chance of a type 1 error. It is useful to distinguish between two error rates. 1, the per comparison error rate, and 2, the family-wise error rate. The per-comparison error rate is the probability of a type 1 error for a particular comparison. The family-wise error rate is the probability of making one or more type 1 errors in a family or set of comparisons. In the attribution experiment just discussed, we computed two comparisons. If we use the 0.05 level for each comparison, then the per-comparison error rate is simply 0.05. The family-wise rate can be complex. Fortunately, there is a simple approximation that is fairly accurate when the number of comparisons is small. Define alpha as the per-comparison error rate and c as the number of comparisons. The inequality shown here always holds true, and the family-wise error rate, or FW, can be approximated as c times alpha. This inequality is called the Bonferroni inequality. The Bonferroni inequality can be used to control the family-wise error rate as follows. If you want the family-wise error rate to be at most alpha, you use alpha divided by c as the per-comparison error rate. So, if you are going to make two comparisons, you use a per-comparison error rate of 0.025. This correction, called the Bonferroni correction, will generally result in a family-wise error rate that is less than alpha. Should the family-wise error rate be controlled? Unfortunately, there is no clear-cut answer to this question. The disadvantage of controlling the family-wise error rate is that it makes it more difficult to obtain a significant result for any given comparison. The more comparisons you do, the lower the per-comparison rate must be, and therefore, the harder it is to reach significance. That is, the power is lower when you control the family-wise error rate. The advantage of controlling the family-wise error rate is that you have a lower chance of making a type 1 error. One consideration is the definition of a family of comparisons. Let's say you conducted a study in which you were interested in whether there was a difference between male and female babies in the age at which they started crawling. After you finished analyzing the data, a colleague of yours had a totally different research question. Do babies who are born in the winter differ from those born in the summer in the age they start crawling? Should the family-wise rate be controlled, or should it be allowed to be greater than 0.05? Our view is that there is no reason you should be penalized, by lower power, just because your colleague used the same data to address a different research question. Therefore, the family-wise error rate need not be controlled. Consider the two comparisons done on the attribution of success or failure data discussed in this section. One tests the difference in attributions after receiving success or failure feedback. The other tests the difference between high and low self-esteem subjects in attributions after success or failure. These comparisons are testing completely different hypotheses. Therefore, controlling the family-wise rate is not necessary. Now consider a study designed to investigate the relationship between various variables and the ability of subjects to predict the outcome of a coin flip. One comparison is between males and females. A second comparison is between those over 40 and those under 40. A third is between vegetarians and non-vegetarians, and a fourth is between firstborns and others. The question of whether these four comparisons are testing different hypotheses depends on your point of view. On the one hand, there is nothing about whether age makes a difference that is related to whether diet makes a difference. In that sense, the comparisons are addressing different hypotheses. On the other hand, the whole series of comparisons could be seen as addressing the general question of whether anything affects the ability to predict the outcome of a coin flip. If nothing does, then allowing the family-wise rate to be high means that there is a high probability of reaching the wrong conclusion. In the preceding sections, we talked about comparisons being independent. Independent comparisons are often called orthogonal comparisons. There is a simple test to determine whether two comparisons are orthogonal. If the sum of the products of the coefficients is 0, then the comparisons are orthogonal. Consider again the experiment on the attribution of success or failure. This table shows the coefficients previously presented in this section to test the two different hypotheses. The column C1 contains the coefficients from the comparison between ratings of people who were told that they had succeeded and those who were told that they had failed. The column C2 contains the coefficients from the test that looked at the difference between the success and failure outcomes for the high self-esteem subjects as compared to the difference between the success and failure outcomes for the low self-esteem subjects. The column labeled product is the product of the C1 and C2 columns. Note that the sum of the numbers in the product column is 0. Therefore, the two comparisons we did in this section are orthogonal. This table shows two comparisons that are not orthogonal. C1 compares the high self-esteem subjects to the low self-esteem subjects. C2 considers only those in the success group and compares high self-esteem subjects to low self-esteem subjects. The failure group is ignored by using zeros as coefficients. Clearly, the comparison of these two groups of subjects for the whole sample is not independent of the comparison of them for the success group. You can see that the sum of the products of the coefficients is 0.5 and not 0.